Here we discuss the relaxation times, the spin-spin relaxation time and spin-lattice relaxation time of NMR. So here for simplicity, we assume a level with nuclear spin half. So therefore, on the magnetic field, there will be two levels. And we have seen that at the equilibrium state, the population of the lower level with population N1 and that of the upper level is related by the expression N2 by N1 is equal to e to the power minus delta E by kT, modulus delta E by kT. So since delta E is very small in the case of NMR, this is very small and can be approximated as 1 minus delta E by kT. So this is approximately equal to 1, and the population of the lower level and upper level are approximately equal to 1 and but slightly less than 1. So N2 is slightly less than N1 at the equilibrium state. And we have also seen that the probability of transition occurring from one spin state to another is directly proportional to the population of the state from which the transmission takes place. So here N2 is slightly less than N1 or N1 is slightly greater than N2. So therefore the transitions from N1, that means absorption, dominate than the transitions from N2. Transitions from N2 means emission. So the probability of absorption and emission are almost equal since N1 and N2 are almost equal, but the probability of absorption slightly dominates. So there is a net absorption of energy when we apply a radiation or electromagnetic state. There will be absorption, and those states in the lower level will absorb energy and go to the higher level by flipping the state. Spin up ആണെങ്കിൽ lower spin up ആണെങ്കിൽ spin down ലേക്ക് പോകും. Spin change ഉണ്ടാവും. Flipping of spin will happen. So ലോവറിൽ സ്പിൻ അപ്പ് ആണോ സ്പിൻ ഡൗൺ ആണോ ഡിസൈഡ് ചെയ്യുന്നത് ന്യൂക്ലിയർ ജി ഫാക്ടറിന്റെ വാല്യൂ ആണ് നമ്മൾ ഓൾറെഡി പറഞ്ഞു. എനിവേ ദർ ഇസ് എ സ്പിൻ ചേഞ്ച് ആൻഡ് at a particular time the N1 will be equal to N2. So due to this net absorption, those states in the lower level will go to the upper level, and at a particular state N1 is equal to N2. So this condition is called saturation. So then the probabilities of the upward and downward transitions are equal since their populations are equal. So therefore no further absorption can take place. So the state is called saturation. But when we observe our NMR spectrum, we cannot observe the change in intensity of the absorbed signal. So it remains a constant. That means there is a population difference always. That means after some time the intensity of the NMR spectral lines. Intensity of the NMR spectral lines means the intensity of the absorbed line will not decrease. So this is due to the fact that the absorbed energy, that means the excited state, is not stable. But in the case of atoms, we know that the excited energy is given in terms of photons by spontaneous emission and stimulated emission, like that. So that is radiated. But in the case of NMR, there is no spontaneous emission. There will be only stimulated or induced emission. And the corresponding spectrum is generally called nuclear induction spectrum. So, when N1 equal to N2, after this is a saturation state. So, from the saturation state, the equilibrium population, that means this thing, where N2 is slightly less than N1, can be re-established if the system loses its absorbed energy by some induced mechanisms. So the mechanisms by which the excess spin energy is shared either with the surroundings or with other nuclei is called the relaxation process. So here the excess energy or the high spin temperature is lost to the surrounding. That means the excess energy is shared by means of non-radiative transitions. That means transitions in which no radiation occurs. So the excess energy is given to the surrounding or lattice by means of some non-radiative mechanism. So the excess energy is lost and the system goes to the equilibrium state. So this transfer of energy from the spin system to other degrees of freedom is called the relaxation. And the time taken for a fraction of 1 by E or 0.37 or 37% of excess energy to be dissipated is called the relaxation time. So the excess energy is dissipated by non-radiative mechanisms, and within some time the excess energy is given back, and the time taken for the 37% of excess energy to be dissipated is called the relaxation time. So there are two types of relaxation processes that can occur for nuclei. One is spin lattice relaxation and the second one is spin relaxation. So in the spin lattice relaxation, the spins in the upper state transfer the excess energy to the surrounding or to the lattice. So this phenomena of where the spins in the upper state transfers excess energy to the lattice or to the surrounding is called the spin lattice relaxation. And the corresponding relaxation time is called spin lattice relaxation time or longitudinal relaxation time. And this relaxation is due to the lattice motion. And this lattice motions have got a particular frequency, and so they interact coherently with nuclear spins. For solids, T1 or longitudinal relaxation time varies from 10 to the power minus 2 to 10 to the power 4 seconds. So T1 ranges from 10 to the power minus 2 to 10 to the power 4 seconds for solids, and for liquids T1 varies from 10 to the power minus 4 to 10 seconds for liquids. So we can see that for solids the relaxation time is slightly higher than that of the liquids. Now we discuss the spin relaxation. So here the excess energy is directly shared between the nuclei via spin relaxation or transverse relaxation. So here the excess energy is given to another spin state. So that state will absorb that energy and flip their spins. So this relaxation is called spin relaxation or transverse relaxation. So the corresponding relaxation time is spin relaxation time or transverse relaxation time. So which is represented by the letter T2, transverse relaxation time. For solids, T2 is of the order of 10 to the power minus 4 seconds, and for liquids, T1 and T2 are approximately equal. T2 approximately equal to T1 for liquid. So we have seen that within this relaxation time, the excess energy is given to the surrounding or to other spins. So the nucleus reach its equilibrium state. So again it can absorb energy. So the process repeats. So if the relaxation time is very long, then the lower state is repopulated at a slow rate. That means if T is very long, it take a very long time so that the excess energy is lost, or the states return to the lower state. So that means the saturation remains for a long time. But if the relaxation time is very small, then the excess energy is easily given to the surroundings and system will go back to the equilibrium position very easily. So in such cases, the saturation position will not remain for a longer time. So the saturation will be lost easily for materials having small relaxation time. We can also explain the relaxation in terms of the population of the lower and upper state. So let N1 as the number of states and the lower state, number of spins occupying the lower state, and N2 is the number of spins occupying the upper state. So in the equilibrium condition, we know that N2 by N1 is equal to e to the power minus delta E by kT, and N2 is slightly less than N1. N2 by N1 is very approximately equal to 1 but slightly less than 1. So N1 and N2 are approximately equal, but N2 is slightly less than N1. So since N1 is greater, there is a net absorption. So when the sample absorb energy, N1 and N2 should change. N1 is the number of state in the lower state. So N1 decreases when the system absorb energy and N2 increases. So the population difference N1 minus N2 is large at the equilibrium point. So when we supply an electromagnetic radiation, then the system absorb energy, and therefore the population difference N1 minus N2 must decrease with time. And at a particular point, N1 minus N2, the population difference become equal to 0 and N1 equal to N2, and this point is called the saturation. But the system will not continue in the saturation for a long time. So the excess energy absorbed by the higher state from the electromagnetic radiation is lost to the surroundings, or it is given to the neighboring spins by non-radiative mechanisms. So N2 decreases again and the population difference increases. So the time taken for the population difference to become 1 over E times the population difference at N t equal to 0 is called the relaxation time. So initially at the equilibrium point, the population difference was maximum, that is n1 minus n2 is equal to n1 minus n1 into e to the power minus delta E by kt. So that is n1 into 1 minus e to the power minus delta E by kt. So this is approximately n1 into 1 minus e to the power minus x. For very small x can be approximated as 1 minus x, 1 minus delta E by kt. So this is the population difference at t equal to 0. So when the system absorb energy, then n1 and n2 should change. So that means more spins will absorb energy and go to the upper state, n2 increases and n1 decreases, and therefore the population difference also decrease with time. So at a particular time, n1 is equal to n2, that corresponds to saturation, but the saturated state will not remain for a long, so the system again loses energy. So those spins, excess spins in the upper state, they will go to the lower state by giving energy to the surrounding. So again after saturation, n2 decreases and n1 increases, and then the population difference also increases after the relaxation. So the time taken for the population difference to become 1 over e times the population difference at t equal to 0. That means this is the population difference at t equal to 0. N of 0 is called the relaxation time. So if it is the relaxation time for spin lattice relaxation, it is called spin lattice relaxation time. Let us calculate an expression for this spin lattice relaxation time T1. So let n is the total number of spins. Assume that n is the total number of spins for a spin half system. So there are 2 levels. So, and n1 represent the number of spins in the lower level, and n2 represents the number of spins in the upper level, and their population difference is given as n equal to n1 minus n2, and the total number of spins is capital N is equal to n1 plus n2, and n2 is the population difference. So n of 0 is the population difference at time t equal to 0, and n of t is the population difference at time t. So we know that the population difference is not a constant, it varies with time, and it is maximum at the equilibrium position. So from these two expressions for capital N and small n1 can be written as, so we have to, for that we have to add these two equations. Capital N plus small n gives 2n1, or n1 can be written as half into n plus small n, where capital N is the total number of spins and n is the population difference. Now let the transition probability per unit time as omega. So that is the transition probability for induced absorption or induced emission. So we know that the probability of transition from a state is proportional to the population of that state. So therefore the probability of transition from the state n1 is proportional to omega n1. So the probability of transition from n1 to n2 is proportional to omega n1, and the probability of transition from n2 to n1 is equal to omega n2. So now dn1 by dt, that is the rate of change of n1 with respect to t. So we know that here n1 is not a constant. N1 changes with respect to time. So as even though n is constant, capital N is constant, small n is a variable. So n1 is also a variable. So n1 changes with time. So we have to calculate dn1 by dt. So n1 changes when there is a transition from n1 to n2, or from a transition from n2 to n1. So dn1 by dt increases when there is a transition from n2 to n1. Number of particles in n1 increases. So that is equal to omega n2 and minus omega n1. So the minus is because the transition from n1 to n2 decreases n1. But the transition from n2 to n1, higher state to lower state, increases n1, but the transition from lower state to higher state decreases n1. So n1 to n2 transition will have a negative sign, since dn1 by dt decreases with this transition, and dn1 by dt increases with this transition. So this can be written as omega into n2 minus n1, but we already know that n1 minus n2 is represented by the letter n, and so therefore this is written as minus omega n. So we can say that the rate of change of population of the state 1 with respect to time is proportional to the population difference as well as the transition probability, and we can see that it is negative initially. So initially it decreases with time. But we have seen that n1 is the average of the total population and the population difference from this expression, and therefore this can be written as d by dt of half into capital N plus small n is equal to minus omega n. So half can be taken out. The total spin is a constant. So in representing total number of spins, so the derivative with respect to time is 0. N is a constant, and therefore d by dt of n plus n is just dn by dt. Half into dn by dt is equal to minus omega n. So the dn by dt is equal to minus 2 omega n, and now we can rearrange this. dn by n is equal to minus 2 omega dt. Now integrating both sides, we get integral of this is log n. Log n is equal to minus 2 omega t plus a constant of integration. So now taking exponentials on both sides, we get e to the power log n is n itself equal to e to the power minus 2 omega t plus c, or into e to the power c. So e to the power c can be taken as a constant. So let that constant is a. So then the population difference, which is a function of time, can be written as n of t is equal to a, the constant a, into e to the power minus 2 omega t. So now we can find a. So we know that at t equal to 0, n equal to n of 0. So substituting this, n of 0 is equal to a into e to the power minus 2 omega into 0, e to the power 0. E to the power 0 is 0. So a equal to n of 0. So n of t is equal to n of 0 into e to the power minus 2 omega t. So where a is n of 0. And now we can plot this. So we have t along x-axis and n of t along y-axis. So at t equal to 0, the population difference is n of 0, which is the maximum value, and then it decreases exponentially, and asymptotically it reaches the x-axis. So this is an exponential decay. So the population difference is maximum at t equal to 0, and then it decreases, and finally it becomes 0. So this point corresponds to the saturation, but the saturated state will not remain for a long. So due to the relaxation process, the excess energy is lost to the surrounding, and some spins in the upper state will go to the lower state by releasing the energy. So therefore n2 decreases again and n1 increases. So the population difference again increases like this. So after saturation, the population difference increases along this curve. And the time taken for the population difference n of t to become the 1 over e times the maximum population. So this is n of 0, and this is somewhat like n of 0 by e, 37% of n of 0, or n of 0 by e. So then the time taken for the saturated state to have a population of 37% of the initial population is called the spin lattice relaxation time here. So this is the T1 over here. So initially at the saturation point, n of t is 0, and after relaxation n of t increases. So the time taken for the state to have a population of equal to n of 0 by e, or 37% of the initial population, is called the relaxation time, and in this case it is the spin lattice relaxation time. So here the energy is lost to the surrounding. So we can calculate T1 from this expression. So we know that n of t equal to n of 0 e to the power minus 2 omega t. So when n of t equal to n of 0 by e, we will get n of 0 by e equal to n of 0 into e to the power minus 2 omega. The corresponding time is t1. So when for the relaxation time, the population difference is equal to 1 over e times the initial population difference. So cancelling n of zeros on both sides, e to the power minus 2 omega t1 is equal to 1 over e, or e to the power minus 1. So from this we can write 2 omega t1 is equal to 1, and t1 is equal to 1 by 2 omega. From here we can see that the relaxation time is inversely proportional to the transition probability per unit time for the induced absorption. So here omega is the transition probability per unit time. Now we discuss the relation between the relaxation time and the spectral line width of NMR. So if for a species having a long relaxation time. So long relaxation time means both T1 and T2 are very large quantities. T1 and T2 are large. So that means it take time for the excited state to go to the ground state, lower state. So an excited nuclear spin go back to the lower state within the relaxation time. So that means the excited state go to the lower state within a time comparable to the relaxation time. So when it is large, that means it takes time for the excited state to go back to the ground state. So that means the lifetime of the excited state delta t is large. Delta t is the lifetime which is of the order of the relaxation time. So we know that from the Heisenberg's uncertainty principle for energy and time, delta E into delta T greater than or equal to cross H by 2. So when the relaxation time is higher, the lifetime of the excited state is higher, and therefore delta T is high. And therefore delta E, the product is a constant, delta E decreases. The uncertainty in energy decreases. We know that E is equal to h nu and delta E is equal to h into delta nu. So when delta E decreases, the uncertainty in frequency also decreases. So this quantity gives the width of the spectral line. So when this decreases, that means the width of the spectral line decreases and we get a narrow spectral line when the relaxation time is higher. For example, if the relaxation time is of the order of 1 second, then delta E into 1 second is of the order of some h by 2 pi. So h by 2 pi means some 10 to the power minus 34 joules. Then the corresponding frequency is delta nu is equal to delta E by h. So which is of the order of some approximately of the order of 0.1 hertz. So this width is very small, and this spectral line width cannot be noticed in usual spectrometers, and it generally appears as a narrow line. So but if the relaxation time is very small, then that means the spins in the upper state go to the lower state very easily within the relaxation time. So the lifetime of the excited state is of the order of the relaxation time. So relaxation time is very small means either T1 or T2 is short. T1 or T2 is short. Then delta T is of the order of the lowest. So then the lifetime is of the order of this, and therefore since it is very small, delta T is very small, the corresponding uncertainty in energy is high. So the corresponding uncertainty in frequency is also high. So for example, if the relaxation time is of the order of 10 to the power minus 4 seconds, so delta T can be also taken as approximately this, and therefore delta E is found to be some 10 to the power minus 31 and all, and delta nu is of the order of some 1000 hertz. So that means we get a broad line. So the line width is there if the relaxation time is very small. So we get a broad line. So we know that in the case of solids, T1 is of the order of 10 to the power minus 2 to 10 to the power 4. But T2 is very, very small. So when T1 or T2 is very, very small, then delta E is very large. So T2 is 10 raised to minus 4 seconds only. So generally for solids, we get broad line spectra. And for liquids, T1 is of the order of 10 to the power minus 4 to 10 seconds, and T2 is also same for liquids. So for liquids having higher value of relaxation time, we get a narrow spectrum, and usually for liquids and gases we get narrow spectrum, but for solids, since T2 is very, very small, we get a broad spectrum. Okay, thank you.